webcast discusses electric current and resistance. We have talked about how objects can have either a positive or a negative charge when they have an imbalance of electrons and protons. When an object has more protons than electrons, it has a positive charge. When an object has more electrons than protons, it has a negative charge. And we know that objects that have like charges, meaning either they're both positively charged or they're both negatively charged, they repel each other. And objects that have different charges, one positive, one negative, they attract each other. Because charged particles exert forces on each other, it's possible to store electric potential energy in a system of charges. And so when we talk about voltage, and voltage is sometimes referred to as the potential difference in a circuit, we're talking about the change in the electric potential energy per unit of charge as the electron moves through the circuit. So as an example, in this figure we see a system of charges where there is an electric field. And I know we haven't really talked much about electric field, but just imagine that we have this bar that has very positive charge, that's in red, and we have another bar which has very negative charge. So if we took a positive test charge, just this circle with the plus in it, it's going to be repelled by that red bar because they both have positive charges. But if I could somehow push that charge closer to the red bar, it'll take work for me to do that because I'm making it do something that is unnatural for the charge. It wants to repel, but I'm pushing it closer. And so the work that I'm doing on the charge is raising the electric potential energy of that charge. And in this figure, you'll see that it's indicated that the voltage where the charge started was at a level of V sub A, and when I pushed it closer to the red bar, the voltage over there is V sub B. That difference in the voltages at those two locations is telling me the amount of work that I had to do per unit charge, which is equivalent to the change in the electric potential energy per unit charge. So when we talk about a difference in voltage between 2 points, that represents the difference in the electric potential energy between those 2 points. The standard metric unit for electric potential difference is the volt, which is abbreviated with an uppercase V. And 1 volt is equal to 1 joule per coulomb, because remember, it's talking about the energy per unit of charge, so joule per coulomb. In circuits work because of the movement of charge and the corresponding change in energy that accompanies that movement. So and we're talking about circuits where the energy is coming probably from a battery. So in the battery, chemical energy is used to separate charges. It moves positive charges to the positive terminal of the battery and transforms that chemical energy into electric potential energy. So the positive terminal is at a high potential, meaning a higher voltage than the negative terminal. Now electrons are the charge carriers, and they move through the circuit from the negative terminal to the positive terminal. Along this path, the electric potential energy gets transformed. Some of it becomes kinetic energy because of the motion of the electrons. A lot of it becomes dissipated energy, especially when the current flows through the devices that are doing something useful for us in the circuit. For example, in a light bulb, the filament becomes very hot and also bright, and so some of the energy is used to cause that heat and light, and we call that dissipated energy. And then when electrons reach the other terminal of the battery, they are ready to begin that cycle all over again. Here's a representation of a very simple circuit that is using a battery to light a light bulb. And so electrons are flowing from the negative terminal around the circuit to the positive terminal. And so the chemical energy in the battery gets transformed to electric potential energy, which gets transformed to kinetic and dissipated energy. Okay, so electric current is the flow of electrons that happens when the ends of a conductor are at different voltages. And when I talk about a conductor, I just mean something that's made out of a conducting material. In a circuit, that would typically be the wires that connect everything in the circuit. And so, you know, in the picture that we were just looking at, the box there, there are wires that are connecting the ends of the battery to the ends of the light bulb. So those would be conductors. And so when there is a difference in voltage between one end of the battery and the other, and they are connected by a set of wires, that means that there is a difference in voltage across the circuit. And that, when you can sustain that difference in voltage, you can cause current to flow. When we talk about electric current, we're talking about the amount of net charge that passes a point in the circuit in a given amount of time. So I, that's the symbol for current, equals the net charge, which is delta Q, divided by the elapsed time, which is delta T. Current is measured in amperes, which is a unit that is has the dimension of 1 coulomb per second. Okay, 1 ampere is 1 coulomb per second, and amperes are represented by an uppercase A. So current is measured in amperes, the net charge is measured in coulombs, and time would be measured in seconds. So I, the current, equals the net charge divided by the elapsed time. So here's an example. So this is showing a large magnification of a wire, and then inside there you can see the electrons which are flowing through the wire, and the blue bar, the vertical line near the center of this wire, that's the point where we are taking a measure. We're counting how many electrons are passing this point in a given amount of time. So they're measuring for 2 seconds. You can see the little clock on the right. And in that time, 1.9 times 10 to the 19th electrons flowed past that point. So we know the number of electrons if we multiply that by the elementary charge, right? Because each electron is carrying a negative 1.602 e to the negative 19th coulombs of charge with it, then we can see that in that 2 seconds there was a net flow of 3 coulombs of charge. And so we could find the current by taking that amount of charge, which was 3 coulombs, and dividing it by the amount of time that it took for that amount of charge to flow past that point. So 3 coulombs divided by the 2 seconds, there was a current flowing through the wire of 1.5 amperes. Let's do one more example. We've measured the current flowing through a wire, and it's 0.4 amperes. So we'd like to know how much net charge is flowing past any point in the wire every second, and also how many electrons are flowing past the point each second. Well, so 0.4 amperes means that there's 0.4 coulombs flowing each second, because an ampere is a coulomb per second. So we know that 0.4 coulombs of charge are flowing past a point every second. And then we want to know how many electrons. Well, we've seen this and used this formula before, that the number of electrons equals that net charge divided by the elementary charge. And so if we do that, we can see that about 2.5 times 10 to the 18th electrons are passing each second. Let's go work a couple of other problems. So I'm in worksheet 9A, and let's see here. I think I will not do number 1. It's very similar to one that we talked about on the slides, but let's look at number 2. We have a current of 1 milliamp. I think I'm going to highlight that. We might need to pay attention to that unit. So this 1 milliamp of current is passing through a copper wire every 60 seconds. So the first thing we want to figure out is how many coulombs of charge are passing through a point in the wire during that amount of time. Well, I'm going to start with the relationship we've just seen, that the current equals the net charge divided by the elapsed time. Now here it looks like we're solving for the charge, so I'm going to get delta Q by itself. The net charge would be the amount of the current times the elapsed time. Okay, so they told me the current is 1 milliamp. I better convert that to amps. I know that milli means 10 to the negative third. So 1 e to the negative third, and that's amperes, right? And an ampere is a coulomb per second, and the elapsed time is 60 seconds. And so when I multiply these, I get 0.06 coulombs. So 0.06 coulombs of charge are flowing past any point in the wire during that time period. And so how many electrons pass any point during 60 seconds? Well, the number of electrons would be that net charge divided by the elementary charge, right? Because the charge is made up. Each electron that flows past is carrying a small amount of charge, and so they all add up to this 0.06. So 0.06 coulombs. The elementary charge is 1.602 e to the negative 19th coulombs. And so when I do that math, I see that there are 3.745 times 10 to the 17th electrons that are flowing past any point in the wire every 60 seconds. And then it says, okay, how many protons are passing any point in the wire? Now be careful. We know that the charge carriers are the electrons. Protons do not move. And so there are no protons passing through that point because the protons do not move. Okay, let's do one more. Number 3, a sensor runs on a current of 0.112 amperes. So how long will it take for 3 microcoulombs of charge to flow through it? Here, it looks like we're looking for the amount of time. It's the same relationship. Current is the net charge divided by the elapsed time, but I'm looking for time, so I'm going to isolate the time. Time would be the net charge divided by the current. Okay, so our charge is 3 microcoulombs. I'm going to convert that to coulombs. That's 3 e to the negative 6 coulombs. The current is 0.112 amperes, and an ampere is a coulomb per second. So if I do this math, I get that it's only going to take 2.679 times 10 to the negative 5th seconds for the 3 microcoulombs to pass that point.